So in chapter 6, we are focusing on calculating the boundary layer, and finally the final output, or the biggest output from the calculation of boundary layer is actually the calculation of direct force. So we will have I would like to share with you some ideas about the direct force and also for the lift force. So because in the beginning of this chapter, we discussed about the shear stress is actually will give us direct force, but if we have a certain angle, so we will have lift force. That's why in aerofoil, we need to make a certain angle of attack to make sure that the lift force can be generated. So in this one, I would like to share with you the idea of the drag coefficient. And because usually we conduct experiment in our lab by using the smooth sphere and with this or smooth cylinder, so we focus on this object because the complicated object is actually not easy to be calculated because sometimes it needs to be curve fitting with the real experimental. So from this graph, you will find that on the y-axis here is the value of CD, and the x-axis here is the value of Reynolds number. So Reynolds number here will reflect the velocity, the velocity of flow. And this CD here is actually the resistance, the drag coefficient that occur for these two types of object, which is the smooth sphere and the smooth cylinder. So this is the smooth circular circle, and the dotted here, okay, is actually for the rough cylinder. So this is for the smooth cylinder. Okay, so and then this is for the rough sphere, and the straight line here is the stream cylinder, and the dotted line here is the stream sphere. So from the boundary layer, so we go for the effect from the boundary layer. So we see about the transition on separation. Okay, so the separation, you know that when the boundary layer is detached from the surface. So let's say from this picture, you will find that for the A here, it's the laminar boundary layer before separation. So you know this is the limit of the separation. So after this, the boundary layer is detached from the sphere. So, and this is the turbulent. So you will find that the limit of the separation here is late. So the lamina is earlier, so it's happened faster compared to the turbulent boundary layer here. So and then this is the first effect that you should know. So and then we call this one another things. Okay, so another thing, if you read about the fluid mechanics, if you read about the creeping flow. So creeping flow is actually the when the Reynolds number is less than 1. So it is the flow that very slow in very small in a small tube or in a small object. So sometimes the Reynolds number is less than 1. So it is a fully laminar, and because it is not easy to it is not comparable with the other flow, so we call it as a creeping flow. So the calculation for the CD for the creeping flow is 24 over Reynolds number, and this equation is almost fixed. Okay, so because the changes is not so different, so we could predict the CD as 24 over Reynolds number. So and then for the creeping flow, so there are no chances for separation to be occur. Okay, so and then so this is the explanation about the above mentioned graph. So for this graph, we will go in a little bit here. So separation is observed at Reynolds number of more than 10 over a very small area on the rear of the body. The separated area increase as the Reynolds number increase. Okay, until the Reynolds number is equal to 1000, where the separated region cease to enlarge. During the growth of separated region, the drag coefficient decrease. So this is actually telling you about this one. So if you have look for this one, so let's say you could read here is 10 by the power of 2, and this is 10 by the power of 3. So which is, this is the 1000 Reynolds number. So you will find that the actually the separation, the area of separation is become larger and larger, so it will give the decrement of drag coefficient. So for both smooth cylinder and also for the smooth sphere, so the drag coefficient is reduced. And then at Reynolds number equal to 1000, 95% of the drag is due to the form drag. The drag force due to the pressure acting on the body, and 5% is due to the frictional drag, which is the drag force due to the shear stress acting on the body. So yeah, I already discussed about this one. So for example, we have a sphere here. So the form drag means the drag that occur because we have the projection area. So we know when there are a pressure change, and then the pressure acts on certain area, so it will create force. So and then the frictional force drag is actually when the flow from here to here. So when it's moving on the surface, it will give us the frictional force. So that's why in a boundary layer, because we are dealing with the drag force, we are dealing with the shear force only. We try to limit the resistance that occur because of the cross-section area. So that's why in boundary layer works, so we only focus on the flat plate. So because we assume that we are now focusing on the shear stress on the surface instead of the thickness of the flat plate. So and then here, when the boundary layer enters the transition region, the value of drag coefficient is decreased for a while. A rough surface will have transition region earlier compared to those with a smooth surface. So this is the idea that we need to understand, because it's based on the experimental observation. So we found that when the boundary layers enter the transition region, so transition means it start to have a turbulent, and then before it's become a fully turbulent, so the value of drag coefficient is decreased for a while after it's become increased again. So a rough surface will have transition region earlier compared to those with a smooth surface. So that's why if we see here, so we found that after the value Reynolds number of 1000 here, so the value of drag coefficient is almost steady. So we assume it's a little bit increased, but it's in steady mode. Okay, so the changes is not fluctuate. It's not so obvious. But for rough cylinder or for the rough sphere here, the drag coefficient will decrease earlier compared to the smooth cylinder or smooth sphere. Okay. So that's why in golf ball, I think it is advantage for you to search about the history of the golf ball and what happened with the golf ball. So the dimple on the golf ball may increase the flight distance by 50 to 100%. So it can double the distance of the golf ball if you use the dimple. So that is the idea of this one. And then we are going for the another phenomenon that called a vortex. So that's why in our chapter 1 to 3 we are focusing on the ideal flow, because in ideal flow we I give you idea. We give you ideas, the importance of potential flow, how to combine the flow, and then why you need to predict the streamline, and then we could predict the vortex, because one element of the ideal flow is we have the vortex. Okay, so why? Because in real situation, in real phenomena, so we found that the flow will create vortex. So for example, we have a long blunt object such as a circular cylinder exhibit a particular interesting phenomenon when placed normal to a fluid flow. Vortices of eddy, region of circulating fluid, are shared from the object regularly and alternately from opposite side as shown below. So the idea is we have an object here, and then we have a perpendicular flow from left to right here. So and then the flow will flow to the like this one, and then because the difference of pressure actually, so the it will get a reverse flow, and the vortex is become here. So and the interesting fact is actually it's occur alternately from opposite side here. So if you could see that it occur here and then it's occur here. So again, it's occur here and so on and so forth. So it is because the pressure is actually fluctuate. So this is the general reason why the vortex become alternate like this one, because the pressure is keep fluctuating. So, and then the resulting flow downstream is often referred as a Karman vortex street, named after Theodor von Karman. So, this is the person who introduced the von Karman integral equation. So, tau is rho u square d theta over dx. That is the von Karman equation. So, the vortices are shared in Reynolds number range 40 to 1000 Reynolds number, and are accompanied by turbulence above Reynolds number equal to 300. So this is the example of the pictures of the vortex shading for the sphere here. So let's say we have a sphere or the cylinder here. So and you could see that the vortex is alternately occur, okay, from this one. So for this one, maybe we have this is the one, this is the one maybe, and this is the one, and then we go here, and so on and so forth. So the vortex, the research about the vortex and so on and so forth is quite interesting, but normally we will base on the experimental works, because the prediction in simulation is actually not enough, not good enough to convince people. But nowadays the computer technology could predict this one, but we still need to compare, we need to validate your coding with the experimental works. So and then the dimensional analysis may be applied to find an expression for the shading frequency, and for high Reynolds number flows, that is flows with insignificant viscous force, the shading frequency F in Hertz depends only on the velocity and the diameter. The shading frequency expressed as a dimensionless quantity is expressed as the Strohal number. Okay, so here I think in our chapter 1, we have one problems about the Strohal number and so on and so forth. So it is the idea is the best way to one of the method that you could apply when you do research is by having the dimensional analysis. So the dimensional analysis will give you certain number that could portray, that could reflect the phenomenon. So the dimensional numbers for the vortex shading is the Strohal number, and the equation is St equal F times d over velocity. So and then why it is important. So I hope at this stage you could see the importance, the importance you need to understand the potential flow, the dimensional analysis that we learned in chapter 1, 2, and 3, because in chapter 4, 5, and 6, when you do the boundary layers, you get the drag force and so on. So the drag force is not the only parameter that we get, because there are another phenomenon that we could get from the boundary layers effect. So one of them is about the shading. So we need to predict, so we need to know the frequency of the shading. Next, I will tell you. So and the common one is the Strohal numbers. So and then this is the common graph to show the range of the Strohal number from the Renault number from the 300s to 10,000 here. So the black line is the experimental data and the blue line is the predicted data from the calculation. So we find that the Strohal number is actually fluctuate at around 0.2, value of 0.2. So if you read back the equation, the question about Strohal number in our chapter 1, so we find that the frequency is actually 0.2. So this is the reason why normally people start to have 0.2 frequency for any uh, situation that may have possibility to swing. Later on, I will show the phenomenon. Okay, so this is the explanation. The engineer or architect must be very careful when designing structures such as towers and bridges that shed vortices. When a vortex is shed, a small force is applied to the structure. If the frequency of shedding is close to the natural frequency or one of the harmonics of the structure, the phenomenon of resonance may occur in which the response to the applied force is multiplied by a large factor. For example, when resonance occurs on a television tower, the deflection of the tower due to the applied force may become so large that the supporting cable fail, leading to collapse of the structure. This has occurred many times, leading to severe damage and numerous deaths and injuries. The collapse of the Tacoma Narrows suspension bridge is undoubtedly the most spectacular failure due to vortex shedding. And also another phenomenon called galloping power line, in which a power line alternates between the usual catenary and an inverted catenary, is another example that may lead to significant damage. This may occur when a power line has eyes up, providing a much larger cross-sectional area for the wind. So there are two ideas. One is about the uh, resonance. Okay, so the common example in so many textbooks about the Tacoma Narrows, and the other one, the simple, because when you build a bridge, this is a very huge structure. So maybe you are the possibility for you to in charge for the big projects here. Okay, you may have possibility of that, but the less the small size of the small scale of example is about the galloping effect. So let's say, for example, this is the Tacoma Narrow Bridge picture. So the bridge here, okay, will swing according to the flow that comes from the side here. So it will create a boundary layer, and then the vortex start to occur, and then the vortex will start to give a frequency a little bit. It start to vibrate a little bit, and then at one point it's combined with the resonance, and then it will create a big fluctuation. So, and then this is the most common one. So this is the galloping wire. So means that why it's happened, because wire, we have a cross sectional like this one. For example, it is around might be 1 centimeters or 2 centimeters. So this is might be the real scale of 2 centimeters or 3 centimeters wire. So and then the flow comes in. So and then you know that the as we learned previously in flow around cylinder, so it's flow, but in real situation the flow is not flowing from this point to this point and then go back to here. So that is the ideal one, means the flow without resistance. So with flow with resistance, so the flow will go like this one, and then it will start to create vortex shadings and so on. Vortex is shading, so it start to create vortex and so on. So and then it start to vibrate. So later on, the frequency is become higher and higher, and it can be interact to each other. It can be touched to each other and start to create a short circuit. So that's why in certain area they will put a stopper like this one, to make sure that if the wire is singing, is moving, it's not, they have no possibility to touch each other and to create any failure. So and then what engineer can do, so we call it as a streamlining. If the flow is to remain attached to the surface of a blunt object, such as a cylinder or a sphere, it must move into regions of higher and higher pressure as it progresses to the rear stagnation point. At sufficient high Reynolds number, mean Reynolds number that higher than 10, the slow moving boundary layer flow near the surface is unable to make its way into the high pressure region near the rear stagnation point, so it separates from the object. Streamlining reduces the high pressure at the rear of the object so that the slow moving flow near the surface is able to negotiate its way into a slightly higher pressure region. The fluid may not be able to make it all the way to the trailing edge of the streamlined object, but the separation region will be reduced to only a small percentage of the initial separated region on the blunt object. The included angle at the trailing edge must not be greater than about 20 degrees, or the separation region will be too large and the effect of streamlining be negated. Drag coefficient for streamlined cylinder and sphere are lower compared to the cylinder and sphere without streamlining. So what is this is about? So this is actually the idea of the ideal flow that we learn in chapter 1 to 3. So I think you already learned in your previous degrees lesson. So the idea is we have a cylinder here. So and then we know that we could predict the streamline by using the ideal flow like this, for example. So and then in real situation we cannot neglect the effect of vortex and another resistance. So the idea of streamlining is why not? Okay, why not from this situation we do a streamlining object, okay, to make sure that the vortex is not too high or the vortex is not too big, so then the streamline will become will smooth the flow. That's why doing the streamlining, the shape of car, whatever, it's actually based on the idea of to prevent the vortex that may be that may increase the possibility of failure. So and then from the cylinder like this one, so we change the shape into this one because we want to cover up, we want to top up the area of vortex here. So this is the idea of streamlining method idea. So and then if you see the first chart, the first table that I show you in this slide, you will find that the streamlined sphere or the streamlined cylinder will give you 50% less of drag coefficient. Another phenomenon that you need to take care about when flow around an object is the cavitation. Cavitation is a very rapid change of phase from liquid to vapor, which occurs in a liquid whenever the local pressure is equal to or less than the vapor pressure. The first appearance of cavitation is at the position of lowest pressure in the field of flow, and 4 types of cavitation have been identified, and it is the traveling cavitation, so the fixed cavitation, the vortex cavitation, and also the vibratory cavitation. So for the traveling cavitation, it exists when vapor bubbles or cavity are formed and swept downstream and collapse. For fixed cavitation, which exists when a fixed cavity of vapor exists as a separated region, the separated region may reattach to the body, or to the separated region may enclose the rear of the body and be closed by the main flow, in which case it is referred as a super cavitation. The vortex cavitation, it is found in the high velocity and thus low pressure core of a vortex, and often observed in the tip vortex leaving a propeller. A vibratory cavitation, which may exist when a pressure wave moves in a liquid. A pressure wave consists of a pressure pulse which has a high pressure followed by a low pressure. The low pressure part of the wave of vibration can result in cavitation. So there are 4 cavitation. So this is the idea of traveling cavitation. So for example, we have a solid body here. So and then we find sometimes we find bubbles start to occur here and its flow down to the downstream there. So it all and the formation of the traveling cavitation. Okay, later on we'll create a fixed cavity or the super cavitation. So the idea is that's why in ideal flow calculation, we are showing you the idea to calculate the pressure on the streamline, because that pressure could predict uh, the pressure could predict the cavitation there. Okay, so this is some pictures of the traveling cavitation. So, okay, so you could see that it start that we have a liquid here, and suddenly the bubble comes because the pressure is become less and less. So and then it start to create a vacuum. So so and then the it's create a bubble there. So and then so it will have there is more from in this picture from left to right. And this is the supercavitation. So the idea is when you have an object here, so for example, you have a bullet here, and this bullet will flow at higher velocity, and then suddenly you will find that the bubble is around the object like this one. So cavitation become a blessing under a condition called supercavitation, when a single cavity called supercavity is formed, enveloping the moving object almost completely. In supercavitation, the small gas bubble produced by cavitation expand and combine to form one large, stable and predictable bubble around the supercavitating object. So this is the common experiment. So for example, we have something like this one, and then we have flow from left to right. So and then suddenly we could create a bubble around the object. So might be the shape of this one is the trigger to have the supercavitation. But sometimes if you have a very fast torpedoes, for example, so you will have this one, so it will create a superlining ideas actually, because it could reduce the drag force. So means that your bullet or your torpedoes will flow, will move faster in water. But for this one, actually, if you do this in water, you need to have a very high speed. So means that maybe you need to have at least Mach numbers velocity. So this is the idea of the idea of the supercavitation pictures. So, and this is the vortex cavitation. It is because of we have the rotationing. We have a rotating device. For example, we have a blade here, and blades rotate at certain speed. Okay, so and then so you could find that the vortex is occur at the tip from the propeller's blade. So this is another example of the cavitation from the tips of blade. And this is the vibration. The cavitation start with the vibration, because we have the fluctuation maybe. So we could see that the graph, the vibration without cavitation is like this one, but the vibration with the cavitation, it shows the acceleration or the fluctuation that are very obvious compared to the no cavitation. So you could see, so this is the without cavitation, and this is the cavitation. So to have the idea for this one, the another uh, dimensionless numbers to calculate the cavitation is we see the cavitation numbers. So it is shown as sigma here. So the first type of cavitation in which vapor bubble are formed and collapse is associated with potential damage. The instantaneous pressure resulting from the collapse can be extremely high, perhaps 1400 megapascal, and may cause damage to stainless steel component, as happened on the propellers of ship. The cavitation occurs whenever the cavitation number sigma is less than the critical cavitation number, sigma critical, which depends on the geometry of the body and the Reynolds number. Here, the P infinity is the absolute pressure in the undisturbed free stream, and PV is the vapor pressure. As sigma decreases below sigma critical, the cavitation increase in intensity, moving from traveling cavitation to fixed cavitation to super cavitation. So this is a few example of CD, and for the Reynolds number 10 by the power of 5. So, and this is the drag coefficient with zero cavitation, and then this is the idea of the critical cavitation number here. So normally for the cavitation and so on and so forth, so we have the angle here. Okay, so because we are using the hydrofoil, so mean we could see that we increase the angle here, so the critical cavitation number is increased, so means that the possibility to have cavitation is increased, because we need to make sure that the pressure is the idea of cavitation numbers need to increase this value. If not, it has possible the cavitation to be occur. Now I would like to discuss about lift and drag on airfoil. So first we go for the separation on an airfoils. Separation occurs on a blunt body, such as a cylinder, due to the strong adverse pressure gradient in the boundary layer on the rear of the body. An airfoil is a streamlined body designed to reduce the adverse pressure gradient so that separation will not occur, usually with a small angle of attack, as shown in the figure below. Without separation, the drag is due primarily to the wall shear stress, which result from viscous effect in the boundary layer. So this is the airfoil here. So usually they try to avoid the separation, because the separation is actually will reduce the lift force. The boundary layer on an airfoil is very thin, and thus it can be ignored when solving for the flow field, the streamline pattern, and the pressure distribution surrounding the airfoil. Since the boundary layer is so thin, the pressure on the wall is not significantly influenced by the boundary layer's existence. Hence, the lift on an airfoil can be approximated by integrating the pressure distribution as given by the inviscid flow solution on the wall. In the next section, we will demonstrate how this is done. In this section, we simply give simple empirical result. So first, we go for the drag force and the lift force. The drag on an airfoil can be predicted by solving the boundary layer equation, simplified Navier-Stokes equation for the shear stress on the wall, and performing the appropriate integration. So this idea is already discussed previously. So we could calculate the existence of shear stress, and then we could calculate the value of boundary layer thickness, and after that we could calculate the drag force and also the drag coefficient. The inviscid flow field must be known before the boundary layer equation can be solved, since the pressure gradient on the wall and the inviscid flow velocity at the wall are needed as input in the solving for the boundary layer flow. For airfoil, a much larger projected area is used, namely the plane area, which is the chord, which is C times the length of the airfoil. Thus, the drag and lift coefficient are defined as this one. So I think this equation is familiar with you, because we already used this one in your undergraduate study, and also I show you this in a previous calculation. So however, because we are focusing on the airfoil, so why we are focusing on the airfoil? Because airfoil is the common object for us to discuss, where it could produce drag and also the lift force. If we discuss with the cylinder or the sphere, so it is not near to the real application, and the angle of attack is not easy to set up for the cylinder or for the sphere. So for the aerofoil here, so we could set up an angle of attack. So when it has angle of attack, so for sure the force will be distributed into lift force and the drag force. And then to calculate this one, so we take the plane area. So the plane area means the chord, mean the length of this distance, the length from here to here. So and then we times with the length of this one. So this is the we call it as a plane area. So this is the common equation for this one is FD is equal to CD times 1 over 2 rho AU square. So in this case, so we take A here as C times L. So what is the beauty of the aerofoil here? Because normally if we use a common shape of object, normally we could say that when the velocity increase, the drag force and the lift force will keep increasing. But for the aerofoil, the impact is when we increase the speed, so the lift force, which is influenced by the angle of attack, so will be increased, but after certain angle, so it is around this one. So after certain angle, the lift force will totally lost. So it will drop immediately. So it's called a stall. So and then for aerofoil, so the we have the conventional aerofoil. So normally conventional aerofoil is stated as NACA 0012 or another numbers of NACA, but sometimes we have a special design aerofoil. So for special design aerofoil, so it might be a little bit different. So normally we are focusing on the conventional airfoil. So this is the conventional airfoil, and it seems that at certain points, so it's the CL and the angle of attack is quite linear increment like this one, but after certain angle, so the lift force will drop immediately. So and then the CD and CL relationship. So this is the coefficient of lift and this is the drag coefficient. So we found that it will curve like this one. And normally people will take the ratio between CD, CL and CD as the indicator. So for a typical airfoil, the lift and the drag coefficient are given in the figure above. For a special design airfoil, the drag coefficient may be as low as 0.0035, but the maximum lift coefficient is about 1.5. The design lift coefficient, a cruise condition, is about 0.3. So cruise condition means when it's not about the takeoff, it's not at the landing mode. So when you fly the flight, so and when after the everything is steady, so you are cruising, so that's called the cruise condition. So the cruise condition, the lift coefficient is about 0.3, which is near the minimum drag coefficient condition. This corresponds to an angle of attack of about 2 degrees far from the stall condition of about 16 degrees. Conventional airfoil are not symmetric, hence there is a positive lift coefficient at zero angle of attack. The lift is directly proportional to the angle of attack but deviates from the straight line function just before stall. The drag coefficient also increased linearly up to an angle to attack to about 5 degrees for a conventional airfoil. Then it increased in non-linear relation with angle of attack. So this is another image that the figure that I could get. So why people need to have a very good streamline, because to make sure that the flow is not detached, there is no separation. So when the angle of attack is become bigger and bigger, the separation start to occur, and when the separation start to occur, so the stall occur, so it will make the lift force drop immediately. So, and then we are going to discuss about slot and flap on the airfoil, because this is actually the a tricks for us to make sure that the area is maintained, and we could get a bigger area from the wing area, and also uh, to make sure that separation is not occur. To take off and land at relatively low speed, it is necessary to attain significant higher lift coefficient than the maximum of 1.7. Or if a relatively low lift coefficient is to be accepted, the area C times L must be enlarged. And both are actually accomplished. Flaps are moved out from a section of each airfoil, resulting in an increased chord, and the angle of attack of the flap is also increased. Slots are used to move high pressure air from the underside into the relatively low momentum boundary layer flow on the top side, as shown in the figure. So we put a flap here. Actually has two function. First is to increase the area, and at the same time we some kind like to make a hole, so the air from the bottom area here, bottom side of the wing, could flow to the upwards like this one. This prevents separation from the flap, thereby maintaining high lift. The lift coefficient can reach 2.5 with a single slot flap and 3.2 with a double slot flap. On some modern aircraft, there may be 3 flaps in series with 3 slots along with a nose flap to ensure that the boundary layer does not separate from the upper surface of the airfoil. The total lift on an aircraft is supplied primarily by the airfoil. The effective length of the airfoil when calculating the lift is taken to be the tip-to-tip distance, the wingspan, since the fuselage acts to produce lift on the midsection of the aircraft. The drag calculation must include the shear acting on the airfoil, the fuselage, and the tail section. The drag coefficient is essentially constant on airfoil up to a Mach number of 0.75. Then a sudden rise occurs until the Mach number reaches unity, Mach number equal to 1. The drag coefficient then slowly falls. Obviously, the condition of Mach equal to 1 is to be avoided. Thus, aircraft fly at either Mach number less than 0.75 or Mach number greater than 1.5. Also, to avoid the high drag coefficient near M equal to 1, Mach number equal to 1. Near Mach number 1, there are also regions of flow that oscillate from subsonic to supersonic. Such oscillation create force that are best to be avoided. So this is the phenomenon that explained previously. So because when the flow is reaching Mach number 1 here, so we found that the drag force is become higher and higher. So it is closely related with the development of Mach cone, and also the development of the air will be compressed at that time. So when the compressed air, so the resistance is increased, so the drag coefficient will be increased too. So it is useful to use swept back airfoil, since it is the component of velocity normal to leading edge of the airfoil that must be used in calculating the Mach number. Cruise speed at Mach number 0.8 with swept back wings are not uncommon. It should be pointed out, though, the fuel consumption depends on power required, and power is drag force times velocity. Hence, fuel consumption depends on the velocity cube, since the drag force depends on the velocity square. Assuming all other parameters are constant, a lower velocity results in a fuel saving, even though the engine must operate longer when traveling a fixed distance. So this is about the discussion between the economical point of view. So might be you could fly slow, so and then it will reduce the drag force, and then you could save fuel. But sometimes you need to uh, make sure that you could reach at certain distance at a certain time. So this is another figure that could show us a few technology that installed in the airfoil to make sure that we could increase the lift force. So this is the CL, the coefficient of lift. So means that we have a few ideas. For example, this is for the airfoil only. And then this is might be for the plain flap. So we have the single, we have a double flap, and then might be we have the additional of boundary layer suction at top of airfoil. So you could see here there is a hole on the wing, so it is going to suck the boundary layer. So it's prevent boundary layer to be separated from the airfoil. So this is another idea of the types of flap and so on and so forth. So as I mentioned previously, so in certain airplane, so they are using triple slotted flap. So this is the a few types and its few advantage. For example, by adding by using compared to the basic foil here, so if we have a flap and then we have a split flap here, so the increment of maximum lift force is 50%, and then this is 60%, and the angle of basic airfoil at max lift is also changed a little bit. So this is might be the highest increment of lift. So it is 90%, and also we have a 90% for the Z flap here. And then we go for the vortex of the airfoil. Fluid particles rotate about the center of a vortex as they travel along in the flow field. There is a high pressure on the bottom and a low pressure at the top side of the airfoil, sketched as shown in the figure below. So we have the schematic sketch of the wing. So let's say this is the wing. Okay, you could imagine this is the wing. This results in a movement of air from the bottom side to the top side around the end of the airfoil as shown, resulting in a strong tip vortex. Distributed vortices are also shared all along the airfoil, and they all collect into two large trailing vortices. On a clear day, the two trailing vortices may show up as visible white streak of water vapor behind a high-flying aircraft. The trailing vortices persist for a considerable distance, perhaps 15 kilometers, behind a large aircraft, and their 90 meter per second vortices can cause a small trailing aircraft to flip over. Also, the trailing vortices induce a downward velocity component that must be accounted for in the design of the aircraft. The tail section is located up high to minimize the effect of this downwash. So downwash is actually the velocity, the downward velocity component that occur on the airfoil. So this is the experimental image to show us the vortices. So might be this using the smoke generator. So tested in a smoke tunnel at certain value of Reynolds number here. So it is the evidence that the vortices vortex at the tip of the airfoil is occur. So this is the another idea to get the location where the vortex is occurred. So it is occur at the tips of the uh, wing here. So and then it will flow like this one. So and then about the downwash here is, so the downwash is actually this the velocity at the end of the airfoil. So the imaginary of the lamina and turbulent boundary layer can be seen in this diagram. So this is the idea. So at certain angle of attack, so engineer may be looking for the inlet angle here and the outlet angle here. So sometimes they call as a upwash angle 55 degree and the downwash angle here is 26 degree. So this is the image of the vortex that actually occur in the when fly at certain speed. So we could see that the cloud here is swirl. So and then this is what the notes mentioned to us, that we could see a thin line of white smoke. So and then this is we could see the clear image of the vortex that occur after a plane fly at certain speed.